Ecco, direi che è partita. Okay. So, so last time we started to do some exercise with the Maxwell-Boltzmann distribution, and I would like to continue with that today. So to finish this exercise, just to show how this formula can be useful to, to solve some problems, and then I will come now to the ensemble theory, which is the core of statistical mechanics at equilibrium. Okay. So we wrote last time. Let me just do a short reminder. So we saw that when I consider the Boltzmann equation and I look for a stationary solution, which means a solution that has not an explicit dependence in time, I get, at least within the assumptions that we did, the Maxwell-Boltzmann distribution, which is the following. It tells me that the distribution function f0 is equal to m divided by 2 pi m kdt square, no, power of 3/2. Then I have, yes, and then of course there is this p squared divided by 2m times beta, where beta is 1 divided by kdp. Yeah. Okay, so just a short reminder. So this was the distribution function, and for what concerns the dimension, this is number of particles divided by volume, which is this density here. This is the particle density, and then I have this. Of course, this is a dimensional, and then I have this quantity, which is energy times mass, which means momentum squared, then square root of momentum squared, power of 3. So then this is momentum to the power of 3, as it should be. Okay, so the dimension of this quantity is this one: number of particles divided by volume divided by momentum to the power of 3. And of course, if I want to compute certain probability that the particle has a certain momentum or a certain velocity within a range, then I have just to do the f0 p dp, which translates, when I introduce the velocity, so p is equal to mv. When I do the calculations, I just need to change the variables and then to introduce the solid angle, and all of these things. Then I get that this quantity, well, if I have to compute, for instance, okay, let me put first this here. So these are n. Then I have a p squared and d squared. So that the exponential, then I have dB, and so then I have a kdt to the power of 3/2. Well, actually, one can also introduce beta here, but it's okay. Then I have a factor of pi divided by 2. So we have 2 divided by pi, and then a mass to the power of 3/2 and dV. Okay, so this is just, if I take this expression, I multiply by dP, I go to spherical coordinates, and that's it. I have a 4 pi, and that's it. So let me check if I have all the numbers in a consistent way. So d squared exponential, the mass goes there. Then we have the kBt, the denominator, and square root of 2 divided by 5. Okay, good. Now, of course, this should be, for what concerns the dimension, this should be now number of particles divided by volume, right? Because I have put this dp, so this quantity here now is number of particles divided by volume, for what concerns the dimension. And if I want the probability, so that now this quantity is proportional to the density of particles. So if I want the probability to have a particle with a velocity with modulus between v and v plus dv, I have to divide by n. So if I do f0 dp divided by n, which is the density of particles, then I have, okay, the same quantity just divided by this. Let me put the factor here, 2 pi, m to the power of 3/2, kT. So this is everything to the power of 3/2 actually. Do a pi, okay, then I have a p squared exponential. Let me write this in terms of velocity, which is the same, and then the dv. Okay, so now this should be the probability distribution for v, which is, of course, is the modulus of the velocity. So if you ask yourself, which is the probability that a particle has a certain value of velocity, v plus d, yeah, between v and v plus dv, then this probability function, density function, is this quantity here. Okay. So let me check if the dimensions are correct, just because it's easy to forget some factor here. So now this is energy, so which means m times v squared, so m simplifies, then I have v to the power of 3, and then I have v to the power of 3, so then it's fine. Okay? So this is the probability distribution, then, that we will use, for instance, to compute what is the average velocity and the most probable velocity if I have a gas with a certain temperature. Of course, I'm talking here about classical particles. So let me write a name here, and I put the word bulk. And in the bulk, this distribution function that we call dn was f0 of p dp divided by n, and this now was equal to, I just repeat the formula as before, 2 divided by pi m divided by kBt to the power of 3/2, the exponential v squared beta, and here I have a v squared and dv. Okay. Yeah. Okay. So the word bulk that I put there is just to indicate the fact that this is the distribution. If I were to look at the situation in which I have a gas in a box in thermal equilibrium, of course, because I'm talking about thermal equilibrium, and I looked for the probability of having a certain velocity. Okay. Now this will be on the right hand side. I will write the same quantity, but in the case of a fusion, and specifically for the case of the sample of particles that exit the box because of the fusion. Okay. So now, with this distribution function, this probability, I can of course write which is the average velocity. And the average velocity, as usual, is just the probability times v. Okay, so it's I can pull out the factors which are constant, and divided by kBt to the power of 3r, and then I have a v cube exponential of v squared times beta, then dv. And I need to integrate this between 0 and plus infinity. Okay? So this will be the average velocity in the bulk. Yeah. So, okay, these integrals are very typical of when dealing with statistical mechanics and kinetic theory. So they are always somehow connected with the Gaussian integral. Okay. So I will not spend too much time on this. If you call alpha the number which is here, so 1/2 m divided by kBt, and that, now this integral is basically the integral from 0 to plus infinity of x squared exponential of minus x squared times alpha dx. And one can compute with standard technique this guy here, and you get 1 divided by 2 alpha squared. And then when I go back to m kBt, at the end the bulk, the average velocity in the bulk, if you just now introduce alpha this formula, one should get this number here. So kBt times 8 divided by m pi. Okay? And this is the average velocity. You can try to calculate this again, but it's about algebra, it should be correct. Well, at least the result is correct, of course. It's taken from a book, but I've done the calculations sometimes, so it should be correct. So let me remove now this, and I want to compute which is the Vp, which is instead the most probable value of the velocity, which turns out, of course, to be different with respect to the average value because the distribution is asymmetric. No? You can make a plot of dn as a function of v, and of course there is a Gaussian tail here when the velocity is large, but for v small this goes quadratically with v, so then I will have a maximum. Okay, so something like this. So now to compute the Vp, now I just need to compute the derivative dn dv. So I have to derive this quantity. Sorry, this made this wrong because we need to write in these terms. So this is the distribution. Okay, so I need to derive with respect to b the exponential m v squared beta times v squared, and then put this equal to 0. Okay. Okay, so you do the calculations again. It's easy, and you get v squared. The most probable value is 2kBt divided by m. Okay. So now all these quantities are defined for the bulk. What I mean with bulk is if I sit, let's say, somewhere inside the box, So this is the distribution function, this is the average velocity, and this is the most probable value of the velocity. So now I can ask myself which are the corresponding values for the flux of particles that exit the box because of the fusion. So I need now to delete all of these, but you can then compare what happens in the flux that exit the box. So the situation was the following, that I have a box with a small hole here, with the size of the hole being much smaller than the mean-free path. Why this is important? Because if the size of the hole is of the order of the mean-free path, or it is much larger than the mean-free path, then I can imagine that when the particles are close to this hole, they actually collide among themselves many times. So then effectively, I will not have any effect of the particle. So I do not see the hole, basically. Okay, the gas behaves in a normal way. The flux of particles is just the same. Okay. So now, let us now write the same quantities. So the distribution of velocity, the average velocity, and the most probable value of the velocity for these particles that goes away. Okay, flux of particles due to a fusion. And we saw last time that, well, basically, I have just to start from the same distribution function, but instead of integrating over the whole solid angle, I need to integrate over a specific fraction of the solid angle because there is a scalar property, B scalar Z. Okay, and then I think that we found last time dj, which is equal to, well, if I want to normalize by the density of particles, I should divide by m. And, but this is not very important. Okay, let me write it this way. So this is a factor of pi, and I have m 2 dkdt to the power of 3/2, all of this. Then I have the exponential, and then I have a PQ times V. Okay, so now, again, so which is the dimension of this quantity here? Well, let me check. So if I put here n, this should be number of particles divided by the volume, this guy here. Then here, what do I have? So here I have again m v squared. So it's a v to the power of 3, which simplifies with this v cubed, and then I have a length divided by time. So here I have a length divided by time. Sorry if I'm doing this, but it's just to check the dimensions are correct. And this is a number of particles divided by volume. Yeah, so this is a length and volume, of course, it gives me a surface. So this is number of particles divided by surface times time, which is the correct dimension of a flux of particles, no? Indeed. Yeah, so we also saw that if I integrate dj over dv, so if I do dj dv dv from 0 to plus infinity, I think we saw last time that we get 1 over 4 and v average, where this v average, it was the average velocity in the bulk. And this relation, so it's telling me that the flux that I have here can be computed as the flux that I would have on a crossing, let's say, a generic surface inside the bulk divided by a factor of 4. That's it. Okay. Yeah. So now I can try to compute also for this sample of particles, which are the average velocity and the most probable value of the velocity. So to compute now, we are within the sample of particles, and if I compute now Vp within the stream of particles, and I compute the most probable value of the velocity, then to get this quantity, I have to again maximize with respect to the v. What? I have to maximize this quantity here, this quantity. So you have to do the derivative with respect to v of v squared e to the minus the usual exponential. I put this to 0, and then I can solve, and I get finally this most probable value of the velocity is 3k dt divided by m. Okay. So you see, and of course it's clear already from the beginning that the most probable value of the velocity is larger, so in the stream, is larger with respect to the same quantity in the bulk. So, of course, so the most probable value in the stream is larger, and similarly, if you compute the average velocity again in the stream of these particles, well, basically this is the integral. If I remove all the normalization constant that anyway we cancel, this is the integral of now this v to the power of 4 exponential divided by the same integral that I put for normalization to the power of 3. Okay. Well, of course, this integral was basically, apart from some constant that is, I do not write because anyway they will cancel, it's just this quantity here. Okay. Apart from constant. Now, if I do again this integral, so the one of before, this was already done. Here I have an additional power of v, so I have a power of v to the 4. So let me maybe remove this. And now this one is basically e to the, sorry, is x to the power of 4. Then I have x squared times, what is this guy? Well, it's always alpha as before. And then here we have x to the 3 minus the squared alpha the x. The final result is that the average velocity in the stream is equal to 9 pi kdt divided by 8 m. Okay. 9 pi kBt divided by 8m, which is again larger with respect to the same quantity in the bulk. So this little calculation basically showing me that when I have the fusion, the average velocity and the most probable value of the velocity of the particle streaming out of the box is larger with respect to the average velocity, the most probable velocity inside the box. And in particular, now this fact, there is also a name for this law that I do not remember now, it's not so important. But as you can see, there I have a scaling here, for instance, for what concern the velocity, the average velocity scales as 1 divided by the square root of the mass of the particle. Of course, at fixed temperature. So now, if I have, let's say, a box with a small hole, and I have here a fusion, but let us suppose that I have, let's say, n1 particles of mass m1 and n2 particles of mass m2, and temperature T, which is common, and I compute the fusion of particles 1 and particles 2, then I will see from this law that the average velocity of 1 divided by the average velocity of 2 must be equal to the ratio, the square root of the ratio of the masses. Okay? And which basically is saying that the smaller the mass, the larger the average velocity, and is also saying that if I look at the stream of these particles, the ones which are let's say the flux, the larger flux is the one of the lighter particles. Okay, so lighter particles will have a larger flux. And therefore, this simple calculation provides, for instance, a technique to separate particles 1 and particles 2. So it's a standard technique, fusion, to separate a mixture of a gas made of a mixture of particles to select one of well, the one that I like more, the lightest or the heaviest. Okay. So this technique, for instance, is used for enriching uranium as similarly to the centrifugal technique. Okay, so now let's do another exercise, in which for the first time now I will introduce time in my problem, which is a quantity that usually do not appear in thermodynamics, because in thermodynamics time doesn't exist in the sense that I'm always at the thermodynamical equilibrium. And so I cannot even ask the question on how much time something will happen. Okay, I just know what happens at equilibrium. But in this case, when dealing with kinetic theory, I can try to solve some of these problems in which also time somehow plays a role. And the associated problem to this is the following. Suppose that I have a volume here with a certain number of particles, n, temperature T, and then again the small hole with a surface S. And of course, I have a stream of particles which want to exit this box. Now, the question I ask myself is, which is the time dependence of temperature? So, how does heat evolves in time due to the diffusion process? So I will have this gas, these particles that will exit the box, and then of course I will reduce the number of particles and also the temperature and also the energy of the particle, the energy inside the box if you want. And then I ask myself how much time, well, how does the temperature evolve as a function of time? I can ask a similar question for how many particles well, for which is the number of particles as a function of time. Actually, I will use this, okay? And then, of course, I'm supposing now here that I have a fusion, of course, and assumption use the ideal gas law for the bulk. So for the gas inside the box, always, so which means that I am imagining that even if I have a fusion, well, I can still apply the ideal gas law, which is correct at the end because at the end the density will actually be smaller and smaller as a function of time. So it's a reasonable assumption. Okay, so now to do this problem, to try to solve this problem, one has to imagine what happens to when the particles flow outside the box, what happens to the internal energy and what happens to the number of particles. Okay, so I can write an equation like this, which is the time derivative of the internal energy, which will be equal to the average velocity, well, to the average energy actually of the particles times dm dt. And this is the average kinetic energy in the for the particles in the stream. So for the streaming particles. And times dm dt, which is the number of particles how does the number of particles change inside the box. Okay. Now again, to compute this average velocity, average kinetic energy, the calculation is basically as before, in the sense that I have a probability distribution for the particles inside the stream, which was this dj, and to compute every probability, I have to use that probability distribution function times the quantity I want to average on, and integrate it over the all values, or the all possible values of v. So then the average energy will be something 1/2 m, and then I will have an integral of course, here I will have v3 dv times v squared. So I have a v to the power of 5 this time. And of course, at the denominator, there is the usual normalization, which is the usual one. I can also compute, this is a matter of days, I can also compute this normalization once and then I keep using the same normalization. But okay, it's the same, doesn't change. And then blah blah. But the idea, of course, is that in this way it's clear which is the structure. No? This is the distribution, so this is the probability distribution times a normalization. And again, here will appear the probability distribution times a normalization that we cancel, and the quantity that I want to average on, which is b squared in this case. Okay. So okay, now you can do the calculation. Of course, now there is a power of 5, which is quite boring. I have not done by myself. I have used Mathematica, to be honest. But you can try to do it if you want, of course. And at the end, it turns out the average energy of the particles is 2k dt. 2k dt. Okay, which is already somehow an interesting result, because you might remember which is the average energy of a particle in the bulk. Does anybody remember this? Of course, yes, most probably, yes. You will remember. You remember the equipartition. We will repeat this, but there is a theorem which is called the equipartition theorem that says that to every degrees of freedom there is a kBt divided by 2 contribution, and so in the bulk this average energy will be the usual 3/2 times kBt, whereas in the streaming this stream of particles is 2 kBt, which is larger, and is larger because we have seen before that the average velocity in the stream is larger with respect to what happens in the bulk. Okay. And so now, okay, so this is the average velocity. So let me remove this quantity here. So this is epsilon. And now I can write the equation du dt is equal to this average velocity, so 2k dt times dn dt, which is telling me that this derivative of u is due to the change of the number of, so the variation of the number of particles inside the box, times the average energy that I'm losing because of fusion. And now this is equal also to, let us remember this quantity that we will calculate later on, but you, of course, you know this, 3/2 mkBt is the internal energy for perfect gas monatomic. Okay, so it's well, it's this 3/2 times kBt, which is the average energy for a single degrees of freedom, for a single particle, times n. Okay, so I can compute this derivative of u with respect to t also as 3/2 kb derivative of t with respect to time. Sorry, I am confusing something. Sorry. So this is 3k, and then of course we have to do the derivative with respect to time of nt. Of course, n changes inside the box, so this was my mistake. And then this is 3/2 kb. Then I have here n dot t plus n t dot. Let me remove this now. Andiamo pure questo. So then this cosa faccio? Semplifico di là. Okay. So this one is 2k dt n dot. Let me put a factor of 4 here. So this is 3kb n dot t plus 3kb and T dot. Then this here, so KB, T and dot, T and dot times T is equal to 3 kBt and T dot. 3 kBt and T dot. Of course, this can be removed. And the derivative of n with respect to time is now equal to 3 times the derivative of temperature with respect to time. Okay. Now let me use also another equation that provides the variation of the number of particles inside the box. And this I know how it works because I know that the flux of the streaming particles, it was 1 divided by 4 times n times the average velocity in the bar. So I can write dn divided by t as, since this variation is, of course, is negative, I can write this as 1 divided by 4 average velocity n, where this guy here is the average velocity in the bulk. So this was the equation that we derived last time. And yeah, so this is a flux, of course. Now it's density times velocity. Then if I want to get a number of particles in time, divided by time, I have to multiply by the surface of the hole. So you have a factor of S, which is the surface of the hole. Okay, which is equal to 1 divided by 4. Then I have n divided by volume, this quantity here. Then I have my surface, and then the average velocity that was computed, and it was 8 kBt divided by m, and there was a factor of 5. 8 kBt divided by m 5. Okay. So now what I will do is to use this equation in here to have an equation for the evolution of temperature as a function of time. Okay. So indeed this equation was telling me that well, dt this was okay, dt divided by okay, let's do the following first. Okay, so dn from here, dn divided by n is minus 1/4 surface 8 kdt and pi, and then I have here t. And of course there is a volume here that is missing. Okay, there is a volume. Let me check if everything is correct. Ma un quarto è ridotto pi greco t, vabbè, questo va bene. And also I know from before that dn divided by n was also equal to 3 dt divided by temperature, sorry, t. And so then basically what I will do is to use now this equation to derive an equation for dt. So dt divided by t is equal to 1/3 minus 1/3. Then I have, okay, I have a factor of 4, s divided by v, and 8 kb t divided by m pi dt. Ok? Va bene, mettiamo il 4 là dentro and then I get come ho fatto lì a mettere il 4 là dentro. Ok, questo viene un fattore di 2. Okay, so let me just arrange this quantity. Now I have a dt divided by t is equal to minus 1/3 s divided by volume, and then I have a square root of kdt divided by 2 m pi, then I have a dt. Vediamo se mi sono messo tutto, S su V e quello a fare là. Ok, cool. Now I can integrate over time and temperature. So let me put here T0 and T, and I call this T prime. And also, well, I have to divide it by T before doing that, to be honest. Ok, facciamolo prima, così, dai. So this is dt divided by t to the power of 3/2. I put this below here, and then it's minus 1/3 as v, and then we have a k v divided by 2 and 5 dt. Okay, so I think now it's almost done. Can now integrate between T0, which is the initial temperature, and T, and this is 0 and T. So prime here, prime here. And then, okay, now it's a matter of calculation. And this is minus 2 T to the minus 1/2 between T0 and T is equal to minus 1/3 S V kV divided by 2 m pi time. Then I will introduce, I multiply by T0 to the power of 1/2 to the left hand side and the right hand side. Then I write you directly the result. I mean, it's just doing some algebra. And the final result is the following. T is equal to T0. And then I have a power law dependence, which is the following, where C is a constant that I have taken to be this quantity here, 6 volume kb T0 divided by 2 pi m. 6 superficie diviso 6 volte il volume, T devo dire qual è. Okay, so I mean, this was just to show that I can try also to solve some let's say, not complicated problems involving also time. I can try to also compute the evolution of thermodynamical quantities as a function of time once I have, of course, the some quantity as the distribution function of the velocity, which is of course much more, let's say, it has much more information than just thermodynamics. Okay. So the Maxwell-Boltzmann, for the Maxwell-Boltzmann distribution, for now it's over, but it will come back later on with some other applications and comments. Consider that here I'm not considering. So when I've written the solution of the Boltzmann equation, I have assumed that there is no external field, so that the force, the external force, is equal to 0. And that's why the system is homogeneous for what concerns the distribution in space, because I have density n, which is the same over in the whole system. If I introduce a force, an external field, this distribution of particles in space will be not uniform anymore. And so this will change my distribution of my distribution function for what concerns velocity and the space distribution, but I will do it in the canonical ensemble, so later on, not now, okay? Just also to use other tools. Okay, so now what we want to introduce now is the theory of ensembles. So, which is the approach to statistical mechanics that was basically devised by Gibbs, and this is the theory of ensembles. We will find, encounter three different kinds of ensembles. Today we will start with the microcanonical ensembles that you have seen already in our, let's say, introduction to statistical mechanics. At least for the system, for a system of localized and independent particles. So so here we will try to introduce the microcanonical ensembles also for particles that are not, let's say, that are free to move in a certain volume and they're not localized. And the situation is more complicated. Okay? Then we will have the so-called canonical ensemble and the grand canonical ensembles that we will do later. Okay, so so the idea, since I will introduce first the microcanonical ensemble, is to take a system for which E, V, and N are fixed quantities. Okay. So the total energy of the system, the number of particles, and the volume are fixed. We will introduce other ensembles in which the energy is not fixed first, and then also the number of particles is not fixed. Okay? But for our initial situation, we will consider this quantity to be fixed. Okay? So now we know, of course, that intuitively, when I fix the total energy, the volume, and the total number of particles in my macroscopic system, of course, there is a high degree of degeneracy for what concerns the position and the momentum of all of the particles inside the system. Okay, so this, of course, is the starting point of statistical mechanics. That, of course, if I take two particles and I just, for instance, exchange their position, or I can, let's say, somehow perturbate the position of a few number of particles or the momentum, basically the overall picture will not change. In the sense that the macroscopic quantities, such as all the thermodynamical quantities, will be the same. So the macroscopic quantities do not depend strongly on what the single particle is doing. Okay, so this is very intuitive. And in principle, of course, this high degree of degeneracy is somehow, is once I fix E, V, and N, is encoded in this number omega, which is the number of microstates, corresponding to same macro state. Okay. Well, I will now define what is the microstate. That depends on the specific problem I'm dealing with. For the case of localized particles, if you remember, the microstate was basically the occupation number of the different energy levels. Once I fix the occupation number of these energy levels, I have my microstate. And we already noticed that, of course, when it's a matter of counting, counting this omega, it could be a difficult task. And but there was another thing that we actually understood is that, and was that when counting omega, actually, and summing over omega, all the possible configuration, what is most important is the most probable configuration. Okay, it's the most probable microstates. So we have done in the past. Okay, so I will introduce a similar quantity now for a system which is not made of localized particles. So I will deal with particles freely moving in a box, which could, in principle, also interact with each other, but this we will see later on. Okay. So now, okay, what is the idea of the ensemble theory? The idea is the following: that in principle, suppose that I have F, which is a certain macroscopic quantity. Vediamo se l'ho chiamato in un certo modo. So suppose that F is a kind of macroscopic observable. For instance, could be the pressure if you want. Okay, I want to measure the pressure of the system. Well, strictly speaking, what we do really experimentally when we measure, for instance, the pressure of the gas, is to put some instrument, of course, and then what we do actually is a kind of time average of F. I have a system, of course, in thermodynamical equilibrium, otherwise I cannot define the pressure. And what I basically do to my measurement consists in a sort of time average from 0 and tau of F T dt. Where tau, of course, must be, let's say, long enough in order to kill all the possible fluctuation of this quantity. Okay, so the measurement process itself is a kind of time average. I put my instrument inside my box, or whatever it is. Of course, if I remove the instrument very soon, after 10 to the minus 10 seconds, I will not have a proper measurement of the system. I need to somehow average on time. So with a time scale tau, that should be, let's say, large enough to provide a good, let's say, a good estimate of the value of F. But in principle, this F is a quantity that is time dependent. So if I consider, for instance, the pressure, now that we know that the pressure is actually provided by the scattering of the single particles between with the wall of my volume, of course, in principle, this is a quantity that depends on time, but I do not care about the complicated variation of time of F. I just need an average. Okay, so this is basically the way to define an observable on a system. Okay, and Now, what is the idea of Gibbs or ensemble theory? Is that basically during this time t tau, sorry, so let's say that between 0 and tau, the system will evolve jumping from one microstate to another microstate. Okay, so the system will change its microstate. So in other terms, it will pick up one of all the possible microstates which are compatible with my macroscopic constraints. So I can have a configuration in which particle 1 is at a certain position initially, and then as time runs, of course, the position of all these particles will change, also the momentum will change. So basically, the system, from the microscopical point of view, will explore all the possible or many possible microstates belonging to this family of microstates, which is highly degenerate. Okay. So then, what I do actually is what I can do is this: the basic assumption of this ensemble theory is that I can substitute. I can compute f not as an average on time, which of course is very complicated because I would need really to follow the evolution of all the particles. Of course, this is not feasible. But to compute this average, not as average, but an average over the possible microstates that belongs to this family with this high number of microstates which are compatible with my macroscopic constraints. Okay, so instead of doing this average, I will actually substitute this average with an average over all the possible microstates, and therefore we'll put something like this. At this level is just a symbol that we are not telling how to compute this number, but just to understand. And then I have a sum over f, not another e of e, where e runs over all the possible microstates. Okay, so this is the basic assumption of ensemble theory. And of course, now there is a hidden here. There is another assumption that I somehow consider. This is typical of the microcanonical ensemble. Somehow I am saying that well, this should be kind of sum or integral of f over a probability distribution function. Okay, and actually we will see in a moment that a typical assumption that is done within the microcanonical ensemble that all the possible microstates are actually equally probable. Okay, but this is a specific assumption that will come in a moment later on. Okay, so but basically, so the idea is to remove this basically this time average because we are not really able to do this time average, and to actually explore for our macroscopic systems which are all the microscopic states corresponding to the same macroscopic state, and then average on these microscopic states. Okay. In this respect, these microscopic states would correspond to elements of an ensemble. It's called ensemble, which are somehow mental copies of the same system. So if I have a chair here, and then I have another chair there, well, sorry, if I basically I'm substituting a time with number, the variation of time with the variation of the possible microstates. Okay, that's basically the idea. Okay, it's the first time that I explain this, so I'm trying to be redundant in order to be sure that you understand what I mean. Okay. So basically, instead of, if I want to compute, for instance, measure the temperature of the chair, instead of putting an instrument here and measure the temperature and average of time, I will take many different chairs that are in the same condition and average over all these mental copies of the chair. Is more or less the idea. Of course, the measurement itself is a time average. The way we compute quantities theoretically, of course, is not a time average. Okay, it must be something more, something different, because we are not able to compute a time average theoretically. Okay. Okay, so now let's start with our system. So let's consider a system of classical particles. Let's suppose that we have n particles. We fix the volume, we fix the energy, and for all of these particles, I can define typical quantities, which are the position or the generalized configuration, generalized position, which are these QE and PE, where EI, runs from 1 to 3n. Okay, which are the quantities that you introduce usually when in analytical mechanics. Okay, so these are the generalized coordinates, if you want. Generalized coordinates, and PI are the momenta, the conjugate momenta, no? Corresponding to this QI. Okay. So basically, I have a vector for QI and a vector for PI. It will be like Q1, Q1, Q2, Q3, blah blah blah, Q3n. And similar for P, P1, P3n. So if I were to work with Cartesian coordinates, for instance, and we do it, Q1, Q2, Q3 could correspond, for instance, to the X, Y, and Z position of the first particle. Then Q4, 5, and 6, the coordinates, Cartesian coordinate of the second particle, and so on and so forth. And now we introduce a space that is called phase space. Lo spazio delle fasi, which I'm sure that you have already seen many times in analytical mechanics, which is a space whose coordinates are all these Q and P. So basically, it's a space, and we call it gamma, in which each point of gamma is a vector having all the components of Q, so Q1, Q, 3n, and all the components of P, 1, 2, 3n. Okay. So if I were to make a plot of the phase space gamma, is a space having as a axis, for instance, here we put Q and here we put P, but of course there are 3n Q axis and 3n P axis, and then we have a point here which is Q, which is in principle a function of time, and P, which is in principle a function of time. Okay. Now, this space, of course, is different with respect to the new space. That was introduced for dealing with the Boltzmann equation, in which case the axes were the three position components and the three components of the momentum. Here instead the axes are all of Q and P. Okay. Now, of course, you know that there is a temporal evolution of P and Q, which is provided by the Hamilton equation. That provides, as I said, the temporal evolutions of these quantities. So Q dot I, where I runs, as I said, from 1 to 3n, is the derivative of H with respect to Pi, where H is the Hamiltonian, of course, Hamiltonian, and it is a function of Q and P. And similarly for P dot I, is the partial derivative of the Hamiltonian with respect to Q I, the minus Q. Okay, and well, what does the Hamiltonian evolution? How do we see what the Hamiltonian evolution does to the system? Well, basically, if I start with a certain vector of Q and P at a certain time, then the evolution, the dynamical evolution of the system will be a trajectory of this point in the phase space whose velocity, the velocity of this trajectory, which means the vector provided by Q dot and P dot, is provided by the relation between these two quantities, which correspond to the components of the velocity in the phase space, and the Hamiltonian. Okay. Now, the Hamiltonian has actually a constraint. Numerically, the Z must be equal to E, which was the total energy. Okay, which is a well-defined quantity in this context. At the end, we will actually somehow interchange between E, which is the total energy, and the internal energy, which are the same quantities in different ensembles. Okay, in this ensemble, basically are the same quantity. Well, actually, the internal energy is something that you define in presence of possible fluctuations, whereas here E is fixed, so it does not fluctuate. Okay. Okay, so well, so a trajectory on the phase space is basically the solution of the Hamilton equation, and there are some features of the trajectory that we might remember. One of the features that trajectory cannot cross with itself, no? So situations like these are avoided, no? If I have a temporal evolution that at some point brings me here, and then I continue the evolution, then at another time it brings me the same point, this would be a problem, no? Because then I have, if I consider this point here, I cannot, I don't know how the system evolves, I have a bifurcation. So these situations are not possible, okay? So once I have a solution of this problem, I do not have, let's say, self-crossing points. And the trajectory, well, so this is impossible. Of course, another thing which is possible instead is the following. If I have a periodic temporal evolution, which could be this is possible. This is periodic. Okay, so I start from a certain time t, and then I just repeat this cyclic evolution, which could be the case, for instance, for the harmonic oscillator. Possiamo pure disegnarlo come un'ellisse, or something like this, no? Harmonic oscillator. Well, for which, of course, the Hamiltonian will be something like this. No? It's a kinetic energy plus a potential energy, which could be well, something like this. So in this axis, in the phase space, the Hamiltonian, well, since this must be equal to the total energy, which is fixed, then this in the phase space, basically the only possible trajectory is an ellipsis, right? For a single harmonic oscillator. Okay? And well, another feature which is somehow clear from well, from the constraints that we have on P and Q is that these trajectories cannot go, let's say, everywhere to some extent. In the sense they are limited, they can explore a limited volume of the whole phase space. Okay. Okay. So this trajectory gamma evolves and within a limited portion of gamma. Why such? But, well, because for what concerns Q, of course, the Q are limited by the volume. If you want, by the size of the box. I think about Cartesian coordinates, no? And then I have, of course, maximum and a minimum size that can that actually is limiting my possible value of Q. And similarly, for the momenta, I cannot have an infinite momentum of the particle, because otherwise I would violate the constraint that the Hamiltonian provides the total energy. Okay, so also PI are limited by well, basically by the square root of the energy times square root of 2m. Okay, so I cannot have a momentum which is larger than the total energy of the system, of course. Okay. Okay, so these are the two features of the trajectories. So they are limited in the phase space. We can explore a portion of the phase space. We do not have any intersection. Well, actually, we can say something more in the sense that this equation is actually the equation h is equal to h, which is a function of q and p equal to v, describe a hypersurface, which has, of course, has a dimension of 6n minus 1, on which lie all which all the trajectories. Okay. So yeah, this is more or less what happens. Now let's start to introduce our ingredients for dealing with the macroscopic systems, in which we are not, of course, taking into account the evolution of all the P and Q, because it will be impossible. And in principle, so what we basically need to get rid of, as I said before, is this temporal dependence of macroscopic quantities. Okay, so at the end of the day, we really not like, we do not like this temporal dependence. Of course, here the temporal dependence is clearly in the evolution, the temporal evolution of P and Q, and every macroscopic quantities will depend on all the values of Q and P at a certain time. Okay, so at the end of the day, we want to remove, to some extent, this temporal evolution. Okay. Now, okay, so now suppose that we are in our phase space, and we have at a certain time the representative point is somehow here. Okay. And now this point here, let's call it Q0 and 0, of course, is consistent with all my macroscopic constraints, no? So Q0 and P0 is indeed a microstate at t equals to 0, consistent with having total energy E, volume V, and number of particles M. Okay. This completely, so if I provide all the values of Q and P at a certain time, my microstate is completely determined. Okay. But now I can imagine that actually there are many points, there is a kind of cloud of points in the phase space which are closer to my Q0 and P0, which actually correspond to the same macroscopic states. So basically the idea is that there is a cloud, if you want, there is cloud around Q0, P0 of points which correspond to the same macroscopic state. And of course, all of these points of this cloud will evolve in time following the Hamiltonian evolution. So if Q0, P0 evolves through this trajectory, all of these points will actually evolve in a similar fashion once I solve the Hamilton equations. And of course, this is in the future if you want, and this was in the past. Okay. So these representative points, which correspond to the same macroscopic states, all of them, of course, evolve in time following the Hamilton equation. Okay. Now, what we define is a kind of probability or as a density of probability, which is defined to be rho, which is a function of Q, P, and T. It is a density in the space gamma, which somehow similar to the probability that we have defined the Maxwell in the Boltzmann transport equation. But actually, that one was in the space mu, whereas here we are in the phase space, which is gamma. But it does more or less the same thing in the sense that it counts the number, basically counts the number of microstates which are the microstates, which are, we say, these microstates belonging to this cloud. Okay. So if I do rho of Q, P, and T times the infinitesimal phase space volume, which would be something like D3mQ and D3mP, this quantity provides, as I said before, the number, okay, the number of microstates, okay, which are again compatible with my macroscopic system. Okay. So somehow the distribution function in the case of Boltzmann is actually an integral, is marginalized, is the marginalization, if you want, of this rho with respect to all of P and Q, which are different from, let's say, 1. Okay, so it's an integral over all the possible momenta and the possible position of all the particles, but for 1. Okay, so this quantity here actually is very, very much full of information in the sense that it contains basically all the information of my system. Okay. Now we can try to do dove stava la cosa, to do what actually was the initial idea. The initial idea was to somehow remove in some way this time dependence when dealing with an observable and actually average over a number of a certain set of microstates. And indeed, once we define this distribution probability, we define F to be it's called ensemble average of a certain quantity, which is F, that could be everything. This is by definition the integral of F, which is a function indeed of Q and P, times this distribution function rho, which is a function of Q, P, and here I write it explicitly, this could depend explicitly on time. Okay, in principle, I could have a dependence on time. I will come to this in a moment. Okay, but to be general, I have to put an explicit time dependence. And then, okay, this integral is done over the phase space, so d3 n q and d3 n p. And now this must be normalized by the same integral without f, which is q, p, and t, d3 n q, d3 n p. Okay. And now, what we have done up to now is just to consider this probability density, and we are defining an ensemble average. Okay. Now, what I'm saying is basically that thermodynamics is provided, well, is recovered when these average are done on a row which does not have an explicit dependence on T. Okay, so at thermodynamical equilibrium, rho is stationary, meaning that the partial derivative of rho with respect to time is equal to 0. And then in this case, indeed, we have exactly the situation that I was, let's say, trying to construct from the beginning, so to have an average which does not depend on time anymore. And indeed, when in the cases in which the derivative of rho with respect to time, the explicit derivative, is equal to 0, we have the situation of thermodynamical equilibrium, similarly to the case in which in the Boltzmann transport equation, we have considered the derivative when the partial derivative of f with respect to time. Also in that case, we were speaking about thermodynamical equilibrium. Okay, so the thermodynamic equilibrium corresponds to a situation in which rho does not depend explicitly on time, and therefore this average here is indeed an average of ensemble, and is not a time. It does not contain, let's say, any temporal dependence. Okay, so we have let's say the situation that we like to have from the beginning. Okay, so now how does we can single out the possible distribution function which do not depend on time? And to do that, we need to do a little to write an equation which is called the Liouville equation. And from that equation, we can see which cases indeed rho does not depend on time, and therefore we are in thermodynamical equilibrium, which is, let's say, if you want, my definition of thermodynamical equilibrium in this context. And then we see which is the possible structure of rho. Okay, so now a question for you. You know what the Liouville theorem is in this context? You have done it in analytical.
Yes, we have done in analytical mechanics, but some students of alcuni l'hanno fatta con la passerina e non so se l'hanno fatta.
Ah, okay. But anyway, I will do it. I mean, it's actually not very difficult to derive this equation, so it's something we can do it easily. So this is the Liouville theorem. So it is basically a conservation law, okay, written in terms of a continuity equation that then can be a little bit simplified by using the Hamilton equation. Okay. So the Liouville theorem is basically the following. Suppose that we have in our phase space P and Q. Let's take a volume omega, is a volume say a portion of the free space omega. Okay. And then suppose that I have now defined this rho, which is this density probability. It is defined as a function of Q, P, and T. And what I want to say first is that if I do the derivative with respect to time of the total number of states which are within this volume, I have to do this integral. So is the partial derivative of rho times the omega over the volume omega, where the omega is the infinitesimal free space volume, which is this quantity here. Okay, so this is what does represent is the variation, the temporal variation of the number of points inside omega. Okay, this is fine because the rho is counting the number of microstates, and this time derivative is just the variation of this total number of microstates inside this volume. Okay, now comes the divergence theorem, if you want, in the sense that what is the flux, the total flux of points which are, let's say, going out of this volume or entering this volume. Okay, so the total flux of points, let's say, crossing the surface of this portion of the phase space omega. Well, this will be, let's call it sigma, the surface of this volume of omega, and the total flux will be something like surface integral over sigma of rho v scalar inverse the sigma in general, where rho is the same quantity. Here is just the usual way to do a surface integral. And v, what is v? V is the velocity in the phase space. So v is a vector, velocity vector, which is provided, as I said before, by the time derivative of Q and P. So here we are in a phase space. A trajectory is the geometric. So it's basically well, it's a parameterization of a curve in terms of Q and P as a function of time, and the velocity of this trajectory is just the time derivative of the components of this vector. Okay, and now these are density times a volume times a surface. Indeed, is providing the total variation of number of points as due to the let's say to the flux, okay, across the surface. Okay, so now this quantity here, by using the divergence theorem, now it is a volume, is an integral over the volume omega, and here you put the divergence of rho v, and it will be in the omega. Okay. Now, this is a typical thing of continuity or conservation. It's a conservation equation which provides a continuity equation, and basically it's telling me that the derivative with respect to time of rho d omega on omega must be equal to minus the flux, the total flux. Okay, it must be equal to integral on the omega of the divergence of rho V and V omega if the total number of points is conserved inside the volume omega. I will come to this point in a moment, okay? So basically, under this equation, now what I'm saying is that inside this volume omega, the total number of points is basically is not changing as a function of time, okay? Now, of course, this can be written in terms of a differential equation, which is the standard continuity equation, which tells that the time derivative of rho plus the divergence of rho v is equal to 0. Okay? Now, this is general, okay? In general, it's just a, let's say, the standard form of a conservation equation. In this case, what I'm conserving is the number of points inside this volume omega. Why I'm saying that this number is conserved? Because all of these points evolves with the let's say with the normal Hamiltonian evolution. So I can think about this volume actually as a sort of volume of liquid which is somehow moving in space, and then I'm not saying anything about the fact that the number of particles in this liquid is conserved. Okay, so this is what I'm saying. So the volume, of course, as due to the evolution of time, could change, could move in space, and could change also the shape, but the number of points is the same. And the reason is that all of these points are actually connected to each other by the Hamiltonian equation, the Hamilton equation. Okay? So all of these points will evolve under the Hamiltonian equation. Okay? And of course, I cannot have, let's say, what enters in this volume exit, so in such a way that the total number of, let's say, of points is the same. So the situation is like a continuity equation for a liquid. So it's similar, in which all the particles moves, all the points of this volume moves following the Hamilton equation. Okay, so now we can rearrange a little bit this continuity equation by using the Hamilton equation and derive at the end what is the middle equation. So I have here the derivative of rho with respect to time plus, so here I have to do what a divergence of rho, and let me write the divergence in these terms. So it's the sum from I to 3n of the derivative of rho with respect to q, derivative of rho with respect to qi, times scalar, if you want, the velocity, which means times qi dot, plus the derivative of rho with respect to pi times the velocity, now which is pi. So here the divergence is acting as a gradient over rho. So if you want, this is the gradient of rho, scalar velocity. Okay, plus, then I have rho, and here I have the divergence of the velocity, so which means the sum from 1 to 3n of derivative of qi dot with respect to qi plus derivative of pi dot with respect to qi. Okay. Now this is equal to 0 due to the Hamilton equations. Why? Because the Hamilton equation was telling me that the Q dot I is equal to the derivative of H with respect to Pi, and P dot I is equal to minus the derivative of H with respect to Qi. So the derivative of Q dot with respect to Qi is actually the mixed derivative of H with respect to Pi and Qi, and the derivative of P dot I with respect to Pi is again the mixed derivative, second derivative of H with respect to Qi and Pi. So therefore this is equal to 0. Okay? Che ne sono? 56. Vabbè, ho finito già. So now this is equal to 0, and this quantity here, I'm left with a quantity which is the rho dt plus sum from 1 to 3n d rho dqi, and q dot is I is the derivative of h with respect to pi minus derivative of rho with respect to pi times derivative of h with respect to qi. Okay? And as due to the continuity equation, this quantity must be equal to 0. Now, what is in the bracket can be written in a more compact way as Poisson brackets, and therefore I have the derivative of rho with respect to t plus the Poisson bracket of rho with h is equal to 0. For this quantity is the Poisson bracket, which is defined as the sum of all degrees of freedom of the derivative of the first quantity with respect to q times the derivative of h with respect to p minus the opposite. No? Now, this equation here is called the Untitled Theorem. And can be written also in terms of a total derivative of rho with respect to time, no? Because this you might remember that if you have a function rho of q, p, and t, the total derivative of this quantity is the partial derivative of rho with respect to t plus the Poisson bracket, which was something that we have done in analytical mechanics. Okay. So basically, the Untitled Theorem is saying nothing but the fact that this rho, the total derivative of rho with respect to time, is equal to 0, and it was obtained by considering the conservation of number of representative points inside this volume, and and then the Hamilton equation. Okay. So now you see that in order, and I will conclude with this. If I want to have thermodynamics, which means thermodynamical equilibrium, which means thermodynamical equilibrium, which is to my intuition is a situation in which I do not see any evolution in time, correspond to the fact that the partial derivative of rho with respect to time is equal to 0, so I do not have any explicit dependence of rho to 0. And now if I use Newville equations, that means that I have a commutation, if you want, with respect to bracket, or some bracket, of rho with h. Okay, so in the situation in which rho let's say commutes with respect to the Poisson bracket with the Hamiltonian, and which means that this is 0, then by using the Untitled Theorem also the partial derivative of rho with respect to time is 0, and I will have my thermodynamics, because in this average of F over the ensemble, actually I do not have any explicit dependence on time anymore. So in some sense, I get rid of time in this situation, no? So that I'm happy because I can recover thermodynamics. And basically, what we'll do next is to consider how, so in which cases this Poisson bracket can be equal to 0. Of course, one simple situation is the one in which rho is a constant, and this would correspond actually to the microcanonical ensemble. Another possibility is that rho is a function of h itself. You can try to show, if you want, that if rho is a function of just h, then the Poisson bracket of rho and h is equal to 0. So you might remember this from analytical mechanics, but you can try to derive this with simple. Okay. So then we will we'll show next time that the rho constant is a possible choice for rho for this ensemble, and this will provide the microcanonical ensemble. Va bene, io direi di fermarci qui, dunque noi giovedì non ci vediamo perché è vacanza, vero?
Esattamente.
Quindi io, diciamo, di sicuro non sono abilitato a venire all'università perché sennò mi multano perché ufficialmente siamo chiusi, però io quasi quasi vi direi di starcene tranquilli. Ci vediamo cos'è che giovedì prossimo, credo. Perché le vacanze sono dal 9
al 15 compreso.
Dal 9 al 15 compreso, quindi io direi, se non ci sono variazioni di programma, tipo se, non so, il direttore di dipartimento ci dice di fare lezione, ma non credo, io direi di rimanere col calendario classico e quindi ci vediamo il 15.
Va bene.
Va bene? Arrivederci.
Arrivederci.
Va bene, grazie.
Vabbè.
Arrivederci.
Allora, interrompiamo la registrazione.